Hey guys, this is Professor Janacek. I want to go over an example where we find the volume of a solid. So remember that volume is going to be the area times the thickness. So let's determine the volume of the solid obtained by rotating the region bounded by y equal to the square root of x, y equal to x squared, x equal to 0, and x equal to 1 about the x-axis. To begin with, I've already graphed this. Just a real quick review of that graph. Y equal to the square root of x is there. Y equal to x squared is there. X equal to 0 is actually the y-axis here, and x equal to 1 is right there. So you can see this little shape here that is bound. That's the region bounded by those equations, and then we're rotating this about the x-axis, and so that gives us the full shape. Another thing you'll notice is I went ahead and selected a little piece here to analyze. That's what we're going to be working with initially. All right, so let's see. Looking at that little piece that we're going to analyze, well, actually, first off, we know that we're revolving about the x-axis. And that little piece that we're looking at, it is perpendicular to that x-axis. Given that information, looking at the notes at the top of the page, revolving about the x-axis, perpendicular to the x-axis, looks like we're going to integrate with respect to x. And we will use a equals to pi r squared for our area. This, by the way, is the ring or washer method. So our volume is, again, area times thickness. The area, we're going to use pi r squared. We'll get to what the r represents here in a sec. And the thickness, remember in all of these situations, the thickness is my differential. In this case, we're integrating with respect to x, so I'll write it as dx. All right, so let's see. Since we're integrating with respect to x, I'll look at my x values. My x values go from 0 to 1. So we'll integrate from 0 to 1. The area, we said, is pi r squared. So let's talk a minute about that radius. If I look at the circles here, what forms a circle? Well, there's an outer circle. Of course, I've got other circles within this. There's circles all the way around there. But looking at this outer circle, what is the radius of this circle? Well, it goes from the x-axis up to whatever my function is. In this case, we do have two functions, but I'm really looking at the y values. So in this case, the radius looks like it's going to be this length right there. That's going to be my outer function minus my inner function. Well, in this case, the outer function is the square root of x. The inner function is x squared, meaning my radius will be the square root of x minus x squared. So back to my formula, I see that I actually need to square those. This is the radius squared. So we have square root of x squared minus x squared squared. Notice we actually have to square them before we subtract in order for this to work. And we have our differential dx there in the back. And ta-da, there we go. That is what we need to integrate. Let's get to it. We can simplify this just a bit. Square root of x squared is just x. X squared squared is x to the fourth. we can take out this pi, and then if we integrate x, we get 1/2 x squared. Integrate x to the fourth, it's 1/5 x to the fifth. Evaluate this from 0 to 1. Shouldn't be too difficult. We have 1/2 minus 1/5 minus, what, 0 minus 0 when it's all said and done, which ends up giving us a volume of, what was that, 3 pi over 10. And there you go. Notice the volume does not have any units on it. This situation does not have any units, but if it did, it would be units cubed. Enjoy!